Hi, I'm Rainer, and this week we're going to talk about a problem involving torques and angular accelerations and tangential accelerations. So in this problem, we've got a little stick that's pinned up here at this corner, and it's allowed to fall down, and it falls a distance theta. And then we take this little point right here, and we say it's a distance x away from the axis. And we say, once the stick has swung down this angle to theta, what is the tangential acceleration of that point? And so here's what we're going to do. When I think of tangential acceleration, I think of alpha times r, where alpha is the angular acceleration of whatever object you're talking about, and r is the distance from the axis of rotation. And so I already know r, it's going to be x, right? That's the distance from the axis of rotation. But I want to find alpha. And so whenever I want to find alpha, usually a good place to turn is to sum the torques. So if I pick a system, and I'll probably say that's a rod, that seems sensible enough, and I'm not going to draw it quite like this. I'm going to draw it already down at that angle theta, because to be honest, when it's up here horizontally, they really have nothing to do with the problem. It's going to swing down, and I know what it did before is going to have no effect on the acceleration. Only the torques and forces at the time are going to decide this. So if we draw like this, and this right here is now theta, I know I've got a weight force, and I'll call that earth on stick. And then I know I've got some kind of pin force coming, so I'm going to draw that at some random angle. I don't know quite where it is. But I don't know anything about that pin force, and I don't want to deal with it. So here's what I'm going to do. I'm going to put my axis of rotation right there. And I'm going to say, well, now there's no displacement between the force and the axis of rotation. And so we're not going to get any torques necessarily. And so now I'll just choose a positive direction and I'll sum my torques. So I chose this way to be positive. And if I sum my torques, I'll end up with something like just mg. I know I can take the force, and then I can multiply that by the distance from the axis of rotation. I know that's something like L over 2. So I should have told you this earlier. We do know that this thing has a length L. And then I know once I take R and I take F, I can multiply it by something like the sine of the angle between them. So maybe I can draw a picture like this and say, if this guy's theta, that must be theta. And then maybe I can say, well, hey, if this is theta, this is definitely also 90. So maybe the angle between, keep in mind, the r vector looks like this, the f vector looks like this. And so this right here is the angle between them. And I'll say that's 90 plus theta. So I'll say sine of 90 degrees plus theta. And so now we've got our sum of torques. I don't know any other forces acting on this system. And I can set that equal to I times alpha. Well, I know for a thin rod that's pinned at its end is 1/3 ml squared. And then I know that alpha is what I'm solving for, so I'm just going to put it in as alpha. And hey, look, the masses cancel, so we don't actually even have to know the mass of the rod. And one of the lengths cancels. And we're left with a pretty simple solution. We can solve for alpha as being g sine of 90 degrees plus theta over 1/3 L, I believe. And this right here is our angular acceleration. We said as soon as we know angular acceleration, let's just multiply it by r, which we said was going to be x. And so I'm just going to say, to replace this with tangential acceleration, I'm just going to throw an x out here. And this right here should be our solution for this problem.